system at an error rate of about 5%. After this error correction, I should say this is the key rate after all this error correction. And it would be, I mean, 500 bits per second or 800 bits per second is not a lot, but it's still enough to just feed your steampunk TT, the typewriters with secret keys, and it's actually good enough for establishing fresh keys for all these AES systems. This is how it looks like on the rooftop, but you just look at the whole thing directly yourself. We are completely running out of time. I should just say there's actually ways to attack that system as well, and maybe I'll just leave that to Antje a little bit to explain how this particular attack works.
Okay, I just rushed through it then. The idea there is that, of course, you can never have the eavesdropper know which detector clicked. If the eavesdropper knows which detector clicked, you're dead. I mean, they know. He or she will know everything there is to know. Now the problem is that you have physically different detectors. In the same way that before, Christian was talking about the different spectral signatures of the lasers used to send the single photons. Now you have 4 different, physically different detectors with slightly different, say, circuits around them. Now, to detect these coincidences, to find these timing correlations, we exchange over a public channel, we exchange all the timing information. Now, the problem is, is there any time signature associated to those APDs, to those avalanche photodiodes, or the associated circuitry? We decided to test this out in one of our, well, in this system actually, and we found the following. So there what you see is the 4 detectors that we're using for the 2 bases, HV 45 and minus 45, and you see that if you take a common 0 of time, they actually react in slightly different times, in slightly different time frames. Now that is, all this information goes through the public channel. So if you listen carefully, you could in principle extract information about which detector fired. And we thought, at first we saw this and we thought, well, I mean, it's not that much. It's maybe half a nanosecond or 300 picoseconds. But it actually turns out that is revealing an extreme amount of information. So if you look at the graph there, you see that with, say, half a nanosecond difference, the eavesdropper knows about 30% of the key exchanged. So you need to be extremely careful with these systems to pay attention to your hardware implementation. There's nothing wrong in the quantum mechanics and the protocol or anything of that sort, but you need to pay attention to these type of things.
And so you have to realize that this timing information really goes over the public channel. So this is a public information with so and so much time for such having a click.
Yeah, this slide here shows actually how you can detect that timing information and try to reveal particular detector combinations in our scheme. Maybe I just skip through that. We will be able to see that online how well these detectors are matched, and we have a few files where we haven't played anything with a timing compensation. So if anybody wants to attack those files, just feel free and try to find out what you can really extract as a secret key. Of course, there's a not so smart cure against that. Is you don't publish that time with that high accuracy. Okay, you just don't say I saw a photon at 5 o'clock and 3 picoseconds. You just say I saw one at 5 o'clock. Okay, so that way you cannot extract that information anymore. But then you need to pay the price in revealing some of the information. Okay, I was told we are hopelessly out of time already, and there's but the following talk is not there, so I'm not exactly sure how we continue. Ilya said we just shamelessly take more time.
No. This I didn't say. I think the next topic is really a kind of we were discussing how to explain it. I think we try to summarize it in a few sentences, and I think it's good if you have interest in this part of the talk to discuss it offline. So I think Christian tried to summarize it already when we were talking about the talk. And I think also in the end, I think there is a little bit of summary and also an announcement for tomorrow, and also where you get the source code and all the background information
the funny thing about that scheme is that now we use all this quantum mechanics to exchange that key, but now you can actually come up with a protocol where you use the measurement results coming out of there, but you don't need to even trust quantum mechanics anymore. That is something.
It's a paranoid physicist.
Yes. So I mean, if there are any physicists around there, in the 1930s, I guess people came up with this complaint that quantum mechanics may not be a nice theory, because it has these stupid random results in it, and it doesn't really tell what is the exact measurement outcome on a single photon, for example. And that led to a lot of discussions. And in the 1960s or so, one chap, John Bell, came up with something where you say, okay, if there's any hidden parameter, and now we translate that into a knowledge of an eavesdropper about a quantum system, then you can construct a mathematical observation and say this quantity, or some combination of measurement results, is always smaller than 2, or the modulus is always smaller than 2. Now, once you assume that there's a knowledge of an eavesdropper, this quantity has to be always smaller than 2. And the trick is you can use this funny quantum state, this entangled quantum state, and that value actually shows you 2 squared of 2, or 2.82 something. Okay? So as long as you see in an experiment this S value of larger than 2, you know there's no knowledge of an eavesdropper about those photon pairs. And you can use this very fundamental, very deep, they say, or whatnot, a property of physics to reveal an eavesdropper. The point is, this Bell inequality was derived by someone who does not use quantum mechanics at all. Okay, so you don't even need to know how the quantum mechanics works, as long as to use that as a knowledge of an eavesdropper, or something which witnesses knowledge of an eavesdropper. As long as you see this S value larger than 2 or smaller than -2, you know that nobody could have listened in that communication. It's a pretty funny game, which also means that you don't need to trust your equipment anymore. At least that's what our theorists say. We of course think, how stupid is this? But nevertheless, we don't understand. We just measure this thing, and it actually looks very similar to the setup we have. So we have some experiments where you just sometimes measure this Bell inequality, or this value, and sometimes you just generate keys. Okay, and I don't know. We just in a lab run over, I don't know, 2 hours or something like that. We generated 10 million bits, and we have this S value here is 2.56, so it's larger than 2. It cannot be due to a photon or a pair where an eavesdropper has a knowledge of some polarization out of it, and the whole thing also works outside. So this is what we typically do. I don't know whether you can see this S here. It's 2.4. Once we bring this thing on the rooftop and go through the atmosphere, it runs overnight here. In the morning, the sun shines. Singapore, I should say, is in the tropics, for those who don't know that. And there's sometimes really hefty rainstorms. So here was a hefty rainstorm, and then they just cannot send light to the other side. The system recovers, and it just generates, I don't know, a few hundred bits per second of secret key. With that, I guess we end this whole session. Apologize for taking way too much time. For those who drink coffee, I guess it's a golden opportunity. Especially for the people who joined this presentation a little bit later on. Tomorrow at 4 o'clock in the afternoon, there's a presentation or a kind of workshop. So hands-on QKD. And actually, we set up the telescopes, and also we have the source over there on this floor, actually close to the first stairway. And we just basically shoot the single photons over the stairway. So I think there's time for questions. Yes, and this was it. I guess that was it. We will put all the source code on this particular website. We haven't done that yet, but I guess maybe this evening or so, all the source code will be open.
Hello.
Thank you.
Okay. A pretty naive question, probably, but how does this work against active man-in-the-middle attacks? Does it work?
It doesn't.
Okay.
Because, well, this man-in-the-middle attacks require some sort of authentication between the two parties. Quantum key distribution cannot offer an authentication. It can only exchange a key between two parties.
So you require some kind of secure channel to set up this secure channel?
Secure channel or an initial secret key. If Alice and Bob have one common secret, they can somehow check whether the key they generated is established between the proper people. So if you want to look at it, this quantum key distribution scheme is actually a key growing scheme. But you do need some initial secret to authenticate. There's a question, I don't know, gentleman in green or somewhere else.
Yeah, my question is,
yeah.
As far as I understand, such entangled systems are very unstable. So wouldn't it be the easiest way for an attacker to just somehow disturb the quantum channel and force Alice and Bob to exchange the information or their key?
Yes, yes. If you want to, I mean, the system is not exactly unstable. Well, I mean, it's kind of this Lego toy thing, and you will get your own opinion how stable it is. But what you can always do is block the quantum channel, both in the entanglement and the Fein coherent pulse systems. That's really the same thing, and force Alice and Bob to exchange. I mean, just use a telephone, say the damn thing doesn't work. Just send me that $1 million via the telephone line.
This just reduces the number of transferred bits to 0.
Yep.
Yeah.
But you will find out.
Okay.
Any questions? So
I might have an idea how to replace your atomic clock. I just heard a talk about the GPS system, and there it came to my attention that actually to define the location you need just 3 signals, but then you need to have an atomic clock within the GPS receiver. In order to get the exact, normal commercial GPS receivers don't have an atomic clock built in, that's why they need the 4th signal. And maybe you could...
Actually, many people use, instead of using atomic clocks, we could use these GPS receivers. And some of our competitor groups actually do that. The nice thing about this system, it's completely independent of any funky clocks. So since this quantum key distribution is about being paranoid to an extreme level, you do not necessarily want to trust an external clock. Because that can give many attack methods. So, but actually I'm pretty convinced you could just run it off a normal crystal clock. That the timing accuracy is good enough for a crystal clock. You just need to know the frequency very accurately.
I have a question about the spectral attack that you presented. How do you actually measure the color if you have just a signal photon?
In the very same way as you measure the color of normal light, you use a spectrometer, just a grating or a prism or something like that, and send or convert that color into a certain direction. And then you put lots of photodetectors behind your grating or the prism, and then one of the photodetectors gives a signal. And
so
then you know.
But then you would destroy the.
That is
photon.
correct. Yeah. That is correct.
So there's nothing special about single photons. You just send it over and over and over again. So and you make this measurement again and again and again.
But if you know which of the 4 diodes were emitting light because you know the color, then you could just make up another photon. So that is. I mean, there are more sophisticated ways of doing that, but that would be the most simple attack. Oh, there's one in the back. Okay.
Thank you. I have 2 questions. The first one is how far can you transmit the signal on an optical fiber without having any amplification? And my second question is, are you familiar with Shamir's large pulse attack, and will that apply in this situation, or will it just be a denial of service?
2 questions. I mean, the first question is how long can you send that photon along? And I guess the longest demonstrations so far are on the order of 100 kilometers. So you have about, I don't know, I have a slide somewhere, but forget about that.